On October 6, 1995, two astronomers in the French Alps pointed a modest telescope at a star so ordinary it had never been given a name, only a catalogue number, 51 Pegasi. They found its light doing something starlight should not do, sliding almost imperceptibly toward blue, then toward red, then back again every 4.2 days like clockwork. Something invisible and massive was tugging on that star in a tight, fast orbit, and the pull could only mean one thing. It was a planet, the first ever confirmed circling a star much like our own sun. This is the story of how that quiet discovery ended a debate that had run for 4 centuries, of the false starts and stubborn skeptics that came before it, of a bizarre first find around the corpse of an exploded star that almost nobody at the time was willing to call a real answer, and of everything that followed, until worlds beyond our own stopped being a hypothesis and became simply the ordinary furniture of the universe. Long before anyone had a way to check, people looked up at the night sky and wondered whether the points of light scattered across it were suns like our own, each with its own family of worlds. In 1584, the Italian friar Giordano Bruno wrote that the stars were distant suns, and that other earths circled them, inhabited by their own kinds of creatures. He had no evidence for this. He simply reasoned that a universe of infinite space, made of the same matter everywhere, had no obvious reason to put planets only around one star and not the others. The Catholic Church tried him for heresy, and among the charges was this picture of countless inhabited worlds. He was burned in Rome in 1600, still refusing to recant it. The idea did not die with him. A century and a half later, the philosopher Immanuel Kant proposed in 1755 that the sun and its planets had condensed together out of a single rotating cloud of gas and dust, a process he thought must be common rather than a one-time event confined to our own solar system. If a star could form this way, he reasoned, so could the planets that came with it, around any star with the right surrounding material. This picture, later called the nebula hypothesis, turned out to be broadly correct. It also implied quietly that most stars in the sky should have planets. But an implication is not an observation, and for the next 200 years nobody had any instrument capable of testing it. This was not simply a modern preoccupation. As early as 1686, the French writer Bernard Lebouvier de Fontenelle published a popular book called Conversations on the Plurality of Worlds, presenting the idea that other stars might have their own planets, as an entertaining, almost scandalous topic for polite conversation rather than settled science. The book was read widely across Europe for more than a century, evidence that the question had already captured the public imagination long before anyone had real evidence either way. By the 19th century, the question had moved from theology into popular science. The French astronomer Camille Flammarion wrote best-selling books arguing that life almost certainly existed on other worlds throughout the galaxy, and the idea captured public imagination even as it remained entirely speculative among working astronomers. Percival Lowell spent a fortune building an observatory in Arizona, chasing what he believed were artificial canals on Mars, evidence, he thought, of a civilization adapting to a dying planet. He was wrong about the canals, which turned out to be an optical illusion produced by the eye trying to make sense of faint, blurred detail. But the broader question underneath his mistake, whether other worlds existed at all, remained entirely open. The trouble was scale. The nearest star beyond the Sun sits more than 4 light-years away, so far that a beam of light, moving at 299,792 kilometers every second, needs over 4 years just to cross the gap. A planet orbiting that star would be a small, dark, reflective speck, sitting directly beside a source of light billions of times brighter than itself. At a distance no telescope of the era could resolve into anything more than a single point. Astronomers could reason their way to the near certainty that planets existed elsewhere. They could not see one, and for a long time they had no realistic plan for how they ever would. That changed, on paper at least, in 1952. The Russian-born astronomer Otto Struve published a short paper pointing out that astronomers had been thinking about the problem backward. Instead of trying to see a planet directly, he argued, they should look for its effects on the star. A large planet orbiting close to its star would tug the star back and forth in a small regular orbit of its own, a wobble that might be detectable in the star's light. And if that planet's orbit happened to be aligned edge onto Earth, the planet would pass directly in front of its star once every orbit, dimming the star's light by a tiny measurable amount. Struve had, in a single paper, described both of the methods that would eventually find nearly every planet astronomers know of today, decades before the technology to attempt either one existed. At the time, his proposal was closer to a thought experiment than a research program. The wobble he described would be almost absurdly small, and the dimming from a transiting planet would be a fractional change in brightness so slight that no detector of the 1950s could register it reliably. Struve's paper sat mostly unread outside a small circle of specialists, but it set the terms for everything that followed. The search for other worlds would not be a search for light reflected off a planet's surface. It would be a search for the faint fingerprints a planet leaves on the star it orbits. Turning that idea into an actual discovery would take the rest of the 20th century, better mirrors, better detectors, and, in the meantime, a string of astronomers who thought they had found something and had not. Struve's insight sat unused for so long, partly because the alternative, actually seeing a planet, looked so hopeless up close. By the middle of the 20th century, astronomers understood the problem in front of them with uncomfortable clarity. A planet does not make its own light. It only reflects a fraction of the light falling on it from its star, and a star outshines any planet orbiting it by an overwhelming margin. The Sun is roughly 1 billion times brighter than Earth as seen from a great distance. Pointing a telescope at a distant star and hoping to pick out a planet beside it is less like searching for a faint object in the dark than like trying to spot a firefly hovering a few meters from a lighthouse from the far side of a bay at night while the lighthouse beam is running directly into your eyes. The difficulty is not only brightness, it is also separation. A planet orbiting another star at roughly the distance Earth orbits the Sun would appear, from many light years away, to sit almost on top of its star from Earth's point of view, separated by an angle smaller than the blur a telescope's own optics smears across a point of light. Even a star's light alone spreads into faint rings and spikes as it passes through a telescope's aperture, an effect called diffraction, and those spreading rings can be far brighter than the planet itself. A planet hiding a hair's breadth from its star, drowned in the star's own scattered light, is essentially invisible to a telescope built to look at the star in the first place. Direct images of planets around other stars would eventually become possible, decades later, for a narrow category of exceptions. Young planets still glowing with the heat of their own formation, orbiting far out from their star, around stars that could be partly blocked out with a specialized instrument called a coronagraph. But those results were still years away in the 1950s and 1960s, and even today direct imaging reaches only a small fraction of the planets astronomers know about. For the vast majority of exoplanets, seeing the planet itself has never been the way it was found. This is why Struve's proposal mattered so much, even before anyone could act on it. Instead of trying to see the tiny dim planet beside the blazing star, astronomers would watch the star alone, and read the planet's presence in how the star's light behaved. A star being orbited by a planet does not sit perfectly still. Star and planet both orbit their shared centre of balance, called the barycentre, and because the star carries almost all of the mass in the pair, that shared centre sits very close to the star's own centre, but not exactly on it. The star traces out its own small loop in space, and as it does, an observer far away sees the star's light shift almost imperceptibly toward blue as it approaches, and toward red as it recedes, a phenomenon called the Doppler effect, the same principle that makes a passing ambulance siren rise in pitch as it nears and fall as it pulls away. Reading that shift requires spreading a star's light out into its full rainbow of colours with an instrument called a spectrograph, then measuring the exact position of the dark lines that specific elements, hydrogen, sodium, iron, stamp into that rainbow wherever they absorb light of a particular colour. As a star wobbles toward and away from Earth, those lines slide back and forth across the spectrographs, read out by an amount that reveals the star's velocity, often to a precision of a few meters per second, slower than a person walking. It took until the 1980s and 1990s for instruments to reach that kind of precision reliably, and reaching it is the whole story of how this search finally succeeded. There was a third approach beside watching a star's light directly, or waiting for a transit. Measuring a star's position on the sky directly, plate after plate, year after year, looking for the same small looping wobble that radial velocity detects through colour, but now traced as an actual physical shift in the star's apparent location among its neighbours. This method, called astrometry, needed no spectrograph, only a telescope, a camera and immense patience, since the shift involved was even smaller on the sky than the width of a coin viewed from many kilometers away. It looked on paper like the most direct and intuitive of the three approaches. It would also produce astronomy's most stubborn false alarm. Small measurements invite small errors, and small errors, chased far enough, can look exactly like a discovery. That trap was waiting for the man who would spend 3 decades convinced he had found the first confirmed planet beyond our solar system. Peter van der Kamp had spent decades at Swarthmore College's Sproul Observatory doing exactly the patient, unglamorous work astrometry demanded, photographing the same nearby stars night after night, year after year, measuring their positions against the background of more distant, effectively fixed stars. His favourite target was Barnard's star, a small, dim and famously fast-moving star only about 6 light-years from the Sun, close enough that even modest position shifts might be within reach of his telescope's decades-old lens. In 1963, van der Kamp announced that Barnard's star showed a small, regular wobble in its path across the sky, and that the wobble matched what a planet roughly 1.5 times the mass of Jupiter, orbiting every 24 years, would produce. It was a sensational claim, the first planet ever detected around another star, found using precisely the astrometric method Struve had outlined a decade earlier. Newspapers covered it, textbooks began including it. Van der Kamp was not a fringe figure making outlandish claims from nowhere. He was a respected mainstream astronomer whose meticulous observing habits over 3 decades were part of what made the claim so credible in the first place. That credibility is exactly why the eventual correction mattered so much. The trouble surfaced slowly. Other astronomers, trying to reproduce his measurements from similar telescopes elsewhere, could not find the wobble he described. In the 1970s, a careful reanalysis found something else instead. A sharp, sudden jump in Barnard's star's measured position that lined up almost exactly with the date the Sproul telescope had its lens cleaned and reinstalled in 1949, the wobble van der Kamp had spent years. Refining was not coming from the star at all. It was coming from tiny, repeatable flexing in his own telescope's optics, a mechanical artifact large enough, at the extreme precision this kind of work demanded, to imitate a planet that was never there. The scale of the error is worth sitting with, because it explains why this kind of mistake was almost inevitable with the equipment available. The apparent wobble van der Kamp measured amounted to a shift on his photographic plates of a few thousandths of a millimetre, smaller than the width of a human hair, translating to an angle on the sky about as fine as measuring the width of a coin from several hundred kilometres away. At that scale, a telescope lens sitting very slightly differently after being cleaned and reinstalled could produce a false signal larger than any real planet was likely to leave. Van der Kamp, to his credit, never fully accepted that his signal was an artifact and continued publishing on it into the 1980s. But the broader astronomical community moved on, and his case became a cautionary tale taught to every graduate student who wanted to search for other worlds. At the very edge of what an instrument can measure, the instrument itself becomes part of what you are measuring. Van der Kamp's was the most famous false alarm, but not the only one. Through the 1970s and into the 1980s, several other astrometric and spectroscopic claims of planets around nearby stars were announced, and then quietly withdrawn or left unconfirmed, as later observations failed to reproduce them. Each failure taught the same lesson. A claim this extraordinary, sitting at the exact edge of an instrument's precision, needed to be checked independently by other astronomers with other telescopes before anyone treated it as real. That standard, more than any single piece of hardware, is what the field was actually missing. When the first confirmed planet beyond the solar system did finally arrive, it would not come from astrometry, or from a star anyone had been watching for decades. It would come from the collapsed, spinning corpse of a star that had already exploded, and a discovery method nobody had originally designed to find planets at all. The discovery method that finally worked did not come from anyone hunting for planets. It came from Alexander Wolszczan, a Polish astronomer studying pulsars, using the enormous radio dish at the Arecibo Observatory in Puerto Rico. A pulsar is what remains after a massive star runs out of fuel and collapses in on itself. A neutron star, an object barely 20 kilometers across but containing more mass than the Sun, spinning many times a second and sweeping a beam of radio waves around like a lighthouse. Every time that beam sweeps across Earth, radio telescopes register a pulse, and pulsars are famous for the almost supernatural regularity of that ticking, some keeping time more precisely than the best atomic clocks humans have built. In 1990, Wolszczan was studying a pulsar catalogued as PSR B1257+12, roughly 2,300 light-years from Earth, when he noticed something odd in its otherwise metronomic ticking. The pulses were not arriving with perfect regularity. They were arriving a fraction of a millisecond early, then a fraction late, in a smooth repeating pattern. Working with Dale Frail at the National Radio Astronomy Observatory, Wolszczan tested a range of mundane explanations: instrumental error, some property of the pulsar itself, a mistake in how the timing was calculated. None of them held up. The pattern that remained was exactly what you would expect if the pulsar itself were being tugged, ever so slightly, back and forth by the gravity of unseen companions orbiting it, the same fundamental idea behind Struve's original proposal, but read out through timing instead of colour. As the pulsar's own tiny orbit carried it a few hundred kilometres closer to or farther from Earth, its radio pulses had a few hundred kilometres less or more distance to cross, arriving correspondingly earlier or later. By carefully modelling that pattern, Wolszczan and Frail worked out that at least two objects were orbiting the pulsar, each with a few times the mass of Earth, in orbits taking roughly 67 and 98 days. They announced the discovery in 1992 in the journal Nature, and it held up. Unlike Van der Kamp's astrometric wobble, this signal was independently checked and reproduced by other radio astronomers using other telescopes, and it kept matching its own predictions years later, exactly as a real orbiting body should. It is worth noting that Wolszczan had, only a year earlier, announced and then quietly retracted an unrelated claim about a different pulsar's companion after further data undermined it. That retraction, rather than damaging his credibility, if anything strengthened the case for PSR B1257+12. This was a scientist willing to withdraw a result the moment the evidence stopped supporting it, and this time the evidence did not stop. By 1994, a third, smaller planet had been found in the same system, and the case was considered closed. These were the first confirmed planets ever detected beyond our own solar system. Full stop. 3 small rocky worlds orbiting a spinning stellar corpse roughly 2,300 light-years from Earth. It was, by any strict definition, exactly the discovery astronomers had been chasing since Bruno's speculation 4 centuries earlier, and it left almost nobody satisfied. The planets circling PSR B1257+12 almost certainly did not exist before the supernova that created the pulsar. The star that became this pulsar likely destroyed any earlier planets when it exploded, and current models suggest these 3 worlds condensed later, out of a disk of leftover debris that fell back around the newly formed neutron star, a second generation of planets born from the wreckage of the first. If that picture is right, these are among the strangest planets known. Worlds that formed not out of a star's original birth cloud, but out of the scattered remains of that star's own violent death. To understand why this triumph felt, to many people, like an asterisk rather than an answer, it helps to understand exactly what kind of object these planets were orbiting, and what it must have taken for them to survive there at all. A neutron star is what is left after a star, several times more massive than the Sun, exhausts its fuel and its core collapses under its own gravity too quickly for anything to stop it, past the point where atoms can hold their normal structure until electrons and protons are crushed together into neutrons packed edge to edge. The result is an object roughly 20 kilometers across, the width of a modest city, containing more mass than the Sun. A single teaspoon of neutron star material would weigh, on Earth, about as much as a mountain. Neutron stars are born spinning, because the star that collapsed to form them was already rotating, and collapsing something smaller makes it spin faster. The same principle that lets a spinning skater speed up by pulling their arms in. A pulsar is a neutron star whose magnetic field channels a beam of radio waves out along its magnetic poles, and if that beam happens to sweep across Earth as the neutron star rotates, radio telescopes see a pulse of energy on every rotation, sometimes hundreds of times a second. PSR B1257+12 rotates roughly 161 times every second, which means its radio beam sweeps past Earth 161 times every second, each sweep arriving with a regularity that rivals or exceeds the best clocks built by humans. For context, the innermost of the 3 planets orbits its pulsar in about 25 days, at a distance from the pulsar roughly comparable to Mercury's distance from the Sun. but around an object radiating none of the gentle warmth of a normal star, only intense radiation and a hostile stream of high-energy particles. Whatever these worlds are like on their surfaces, they are not going to look like anywhere in our own solar system. That regularity is precisely what made the planets detectable. Radial velocity at the time could only measure a star's speed to within a few hundred meters per second, nowhere near precise enough to catch the subtle tug of an Earth-sized planet on a Sun-sized star. But a pulsar's timing could be measured to within millionths of a second, and a companion with only a few times the mass of Earth was enough to shift the pulsar's tiny orbital position by an amount that translated into a timing delay well within reach of that precision. In effect, the extreme regularity of the pulsar's clock did the job that a far more sensitive spectrograph would eventually need to do for ordinary stars. It turned an invisible gravitational tug into a measurable repeating signal. Pulsar timing carries its own risks of false alarms, and Wolfsjan was aware of them from his own earlier retracted claim. Anything that changes a pulsar's internal structure even slightly, a phenomenon called a glitch, in which the crust of the neutron star suddenly settles and the spin rate jumps, can imitate part of a timing signal. What separated the confirmed planets around PSR B1257+12 from a glitch or an instrumental error was the shape of the signal. It was periodic, repeating on the same schedule year after year, in a pattern consistent with Newtonian gravity, and multiple orbiting bodies tugging on each other in ways that could be checked mathematically against future data. It kept predicting its own future behavior correctly. A glitch does not do that. The physics held up completely. What did not settle so easily was the argument over what these three small worlds should be called, and whether finding them counted as answering the question people had actually been asking since Bruno first raised it. The planets around PSR B1257+12 satisfied the strict scientific definition of the word discovery. They were real, confirmed, independently verified orbiting bodies smaller than stars, and they arrived first. But quieter argument ran alongside the celebration. Pulsar planets, whatever they were, felt like a technicality to the broader question everyone actually cared about. The centuries-old question that had driven Bruno, Kant, and every stargazer since was never really, are there planets somewhere? Full stop. It was a more specific and more personal question. Is our solar system typical, or are we some kind of cosmic accident? Are there other worlds out there that resemble our own, orbiting stars that shine steadily for billions of years the way the sun does, giving any planets around them the stability that life, as far as anyone knew, seemed to require? A planet orbiting a pulsar could not plausibly answer that question. Pulsars are bathed in radiation far more intense than sunlight, and any planet close enough to be detectable in the pulsar's timing was almost certainly too hostile an environment for the kind of chemistry life on Earth depends on. The contrast is worth making concrete. The sun has shone with roughly its current brightness for about 4.6 billion years, and will continue doing so, changing only slowly for billions more, plenty of time for complex chemistry, and on at least one occasion, life to develop on a planet orbiting it in relative peace. The star that became PSR B1257+12, by comparison detonated in a supernova so violent it would have sterilized or destroyed any planets that existed beforehand, and the neutron star left behind still floods its surroundings with radiation that would be lethal to anything like Earth's biosphere at a similar distance. A civilization looking for somewhere to plant a garden would choose the sun's kind of star every time. Through the 1980s and into the early 1990s, several teams around the world were racing toward exactly this goal, refining the radial velocity method. Struve had sketched decades earlier until it could reliably detect a star's wobble down to a precision of just a few meters per second. A Canadian team led by Bruce Campbell and Gordon Walker pioneered some of the earliest high-precision techniques in the early 1980s. In the United States, Jeff Marcy and Paul Butler built one of the most sensitive radial velocity programs of the era at Lick Observatory in California. And in Switzerland, at the Observatoire de Haute-Provence, a small team led by Michel was building its own instrument, one that would ultimately reach the finish line first. Every team involved understood the shadow Van der Kamp's error still cast over the field. A claim this significant would not be believed on the word of a single observatory. It would need a signal that repeated cleanly across many nights and many years, that matched simple physical predictions about what a real orbiting planet should do, and ideally confirmation from an entirely separate team using entirely separate equipment before anyone treated it as settled. That caution, hard won over 3 decades of false starts, was about to be tested by the most consequential few weeks any of these teams would ever have. It was the Swiss team, working with a smaller telescope and a newly built spectrograph named ELODIE, that got there first, and what they found would turn out to be stranger than any of them expected. Michel was an established astronomer at the University of Geneva, known for his work on and motion of stars within the Milky Way when he turned his attention toward the planet search in the 1980s. He was joined by a doctoral student named Didier Queloz, who would spend much of his graduate studies helping build and refine the very instrument that would make the discovery. Their instrument, named ELODIE, was installed on a 193-metre telescope at the Observatoire de Haute-Provence, in the hills of southern France, a telescope modest by the standards of the era's largest observatories, but paired with a spectrograph built specifically to chase the radial velocity signal Struve had described. ELODIE spread a star's light into its full spectrum and compared it, in the same instrument, against the light from a reference lamp with precisely known wavelengths, allowing it to detect a shift in a star's spectral lines corresponding to a velocity change of roughly 13 meters per second, a little faster than a brisk walking pace. That was, at the time, among the most precise velocity measurements ever achieved on a star. Starting in 1994, Mayor and Queloz began systematically monitoring 142 stars similar to the Sun, returning to each one repeatedly over months, recording its spectrum each time and watching for the smooth, periodic shift in its spectral lines that would mean something was tugging on it. It was slow, repetitive work, and most of the stars showed nothing at all, their spectral lines sitting essentially still from one observation to the next, the way most stars were expected to behave if they had no massive nearby companion. Each star on their list had until that point been nothing more than a point of light in a catalogue, one among the roughly 6,000 stars visible to the naked eye from Earth, and billions more too faint to see without a telescope, indistinguishable from its neighbours except by a number and a position in the sky. Mayor and Queloz's work was, in effect, a search for the one star among many whose light was quietly announcing that it was not alone. One star stood out almost immediately for the wrong reasons. 51 Pegasi, a star about 50 light-years from Earth in the constellation Pegasus, similar in mass and in temperature to the Sun, showed a wobble, but a wobble that repeated far too quickly to make sense under the assumptions the team had built their search around. Most planet searches at the time were designed with something like our own solar system in mind, where the closest large planet, Jupiter, takes about 12 years to complete one orbit. A 4-day cycle looked, at first glance, more like a problem with the instrument or with the star itself pulsating than like a planet. Queloz spent months trying to rule out every explanation other than a planet. He checked whether the star itself might be vibrating in some way that mimicked an orbital signal, a known complication for certain kinds of stars. He checked the instrument's calibration against reference stars known to be stable. Every test came back the same way. The signal was real, it was clean, and it repeated with almost perfect regularity every 4.2 days, exactly the kind of consistency a real orbiting body, and nothing else, tends to produce. By the summer of 1995, the team was confident enough in the signal to start asking what kind of object could possibly produce it. An object close enough to its star to circle it once every 4 days, and heavy enough to move a star the size of the Sun by a measurable amount. With a clean repeating signal in hand, Mayor and Queloz could do more than confirm that something was orbiting 51 Pegasi. The shape and size of the radial velocity signal, plotted over time, carries specific, calculable information about the thing producing it, in the same way that the pitch changes of a passing ambulance siren tell a careful listener something about how fast the ambulance is moving, even with their eyes closed. The most direct piece of information is the orbital period itself, the time between one full wobble and the next, which in 51 Pegasus' case was 4.2 days. Nearly 3 centuries earlier, Johannes Kepler had worked out a precise mathematical relationship between an orbiting object's period, its distance from what it orbits, and the mass of the thing it orbits, a relationship still called Kepler's third law. Knowing 51 Pegasus mass, which could be estimated from its temperature and brightness compared to other stars like it, and knowing the orbital period from the radial velocity data, Mayor and Queloz could calculate the orbiting object's distance directly. The answer came out to about 0.05 times the distance between Earth and the Sun, roughly 1/20th of that distance, meaning the planet was orbiting more than 7 times closer to its star than Mercury orbits the Sun. The second piece of information comes from the size of the star's velocity wobble, how fast the star itself moves back and forth. A more massive orbiting companion pulls harder on its star and produces a bigger wobble. A lighter one produces a smaller wobble. To put the wobble itself in human terms, imagine the Sun 1.4 million kilometers across being tugged back and forth by an unseen planet at a top speed slower than most people can jog. That is the entire physical signal Mayor and Queloz were reading. It's a star far larger than anything in ordinary experience, moving by an amount too small to see with any eye, changing the colour of its light by a fraction so small it required one of the most sensitive spectrographs on Earth to notice at all. From the amplitude of 51 Pegasus wobble, roughly 56 meters per second, well within ELODIE's precision, Mayor and Queloz calculated that the object tugging on the star had to have at least about half the mass of Jupiter, the largest planet in our own solar system. That number came with an important caveat, the kind every radial velocity measurement carries. The method reveals a minimum mass, not a guaranteed one, because it cannot fully account for the unknown tilt of the orbit as seen from Earth. Only later observations using other methods would narrow that uncertainty down. Put together, the numbers described something that did not resemble anything in our own solar system. An object with roughly half the mass of Jupiter, orbiting its star once every 4.2 days, at a distance where, if you placed it in our own solar system, it would sit closer to the Sun than Mercury. Every giant planet astronomers had ever studied up close, Jupiter, Saturn, Uranus, Neptune, orbited its star slowly at a comfortable distance, out where the material to build a planet that large was thought to be abundant and cold enough to condense into ice and gas. Nothing in the accepted theory of how planets form predicted a Jupiter-sized world sitting in an orbit that tight. Mayor and Queloz understood immediately that this result, if it held up, was going to be controversial for reasons well beyond the ordinary caution surrounding any new planet claim. It was not simply a matter of whether the signal was real. It was a matter of whether the object being described could exist at all, according to everything astronomers thought they understood about how planets form. They ran the checks one more time, confirmed the signal held across further observations that summer, and decided the result was solid enough to bring to the rest of the field. Through the summer of 1995, Mayor and Queloz kept returning to 51 Pegasi with ELODIE, watching the same 4.2-day cycle repeat itself with a regularity that never wavered. By early autumn, the signal had held across dozens of separate nights, tracing the same smooth curve of blue shift and red shift over and over, exactly what a stable real orbit should look like, and exactly unlike the erratic, changing patterns that would suggest some quirk of the star itself. To grasp how strange that 4.2-day period really was, it helps to set it beside the planets we already knew. Mercury, the innermost planet in our own solar system, takes 88 days to complete one orbit of the Sun. Earth takes 365. Jupiter, the giant planet 51 Pegasus' newly discovered companion most resembled in mass, takes almost 12 years. The object orbiting 51 Pegasi completed a full circuit in barely more time than it takes the Moon to complete about a seventh of its own orbit around Earth. Whatever this planet was, it was living an entire year, by its own clock, roughly every 100 hours. The team submitted their result to the journal Nature in September 1995. It moved through peer review with the kind of scrutiny any claim this significant demanded, other astronomers checking the mathematics, questioning the assumptions, looking for any alternative explanation the authors might have missed. The paper was accepted, and the timing lined up with an already scheduled astronomy conference in Florence, Italy, in the first week of October, an unusually public stage for what was about to become one of the most significant announcements in the field's history. Mayor and Queloz were careful, in their own paper and in their early remarks, not to overclaim. They described the signal precisely, laid out the alternative explanations they had ruled out, and stated plainly what the data did and did not prove. They knew the field's history well enough to expect that some astronomers would want to see the result reproduced by an entirely separate team, with entirely separate equipment, before treating it as beyond doubt. That confirmation, as it turned out, would arrive within days of the announcement, not years, a sign of how far radial velocity technology had come since Van der Kamp's era. There was also, quietly, a sense among the team that they might be looking at something categorically new, not merely the first confirmed planet around a star like the Sun, but a kind of planet nobody had previously imagined existing anywhere. Every theoretical model of planet formation available in 1995 assumed that a Jupiter-sized world needed to form far from its star, beyond a boundary sometimes called the frost line, where ices could condense out of the disk of gas and dust surrounding a young star. An object with half of Jupiter's mass sitting closer to its star than Mercury sits to the Sun had by that logic no reasonable way to have formed where it currently orbited. But before the confirmation came the announcement itself, and the announcement raised a question that mattered just as much as whether the signal was real. If it was real, what kind of world could possibly exist in an orbit that fast, that close, and that hot? The planet orbiting 51 Pegasi, which came to be named 51 Pegasi b, following the astronomical convention of labelling a star's planets alphabetically starting with B, presented theorists with a genuine puzzle. Every model of how planets form, built up over decades from observations of our own solar system and of young stars still surrounded by disks of gas and dust, agreed on one basic point. Giant planets built mostly of gas needed cold conditions and an abundant supply of ice and gas to grow large, conditions that existed only far from a star's heat, well beyond the orbit of a rocky inner planet like Earth or Mars. Astronomers call the boundary where it becomes cold enough for ices to condense out of a swirling disk of gas and dust the frost line, or sometimes the snow line. In our own solar system's early history, that boundary sat somewhere around where the asteroid belt lies today, several times farther from the Sun than Earth. Beyond it, the outer planets, Jupiter, Saturn, Uranus and Neptune, had access to enough icy material and enough raw gas to grow into giants. Inside it, only smaller rocky worlds like Earth, Venus, Mars and Mercury could form. Because the available raw material there was scarce and mostly non-icy. 51 Pegasi b orbited more than 7 times closer to its star than Mercury orbits the Sun, deep inside where the frost line should have been for a star like 51 Pegasi, a region where the standard theory said a gas giant simply could not assemble itself. There were only 2 ways to reconcile the observation with the physics. Either the theory of planet formation was fundamentally incomplete, or the planet had not formed where it currently sat, but had migrated there after forming farther out, spiraling slowly inward over millions of years through gravitational interactions with the leftover disk of gas around its young star. The migration explanation, developed rapidly by theorists in the months after the discovery, holds that a young giant planet, while still embedded in the disk of gas and dust it formed from, can lose orbital energy through friction and gravitational drag with that surrounding material, causing it to spiral gradually inward toward its star over the course of a few 100,000 to a few million years, a blink of an eye compared to a star's multi-billion-year lifespan. Exactly what stops the planet from spiraling all the way into the star and being destroyed, whether it is the inner edge of the disk itself, or the star's own magnetic field, or some combination of forces, remains an active area of research, and different theoretical models offer somewhat different answers. What is far less contested is that migration of some kind has to have happened. A planet like 51 Pegasi b could not plausibly have formed in place. Astronomers began calling this new class of object a hot Jupiter, a gas giant with roughly the mass of Jupiter or more, orbiting so close to its star that its outer atmosphere is heated to temperatures well over 1000 degrees Celsius, hot enough to glow visibly if it were close enough to observe directly, its winds howling at speeds far beyond anything recorded on any planet in our own solar system. It was, in a strange way, a humbling discovery before it was even fully confirmed. The very first exoplanet found around a Sun-like star was not a twin of Jupiter sitting comfortably in a Jupiter-like orbit. It was a planet unlike anything humanity had ever seen up close, immediately proving that our own solar system's particular arrangement, small rocky worlds close in and giant gas worlds far out, was not necessarily the universe's default pattern. That was the world Mayor and Queloz carried to the stage in Florence, not simply a new planet, but a challenge to the field's basic assumptions about how planetary systems were supposed to look. On October 6, 1995, Michel presented the discovery of 51 Pegasi b to an assembled room of astronomers at a conference in Florence, Italy. The reaction in the room was, by multiple accounts, a mixture of genuine excitement and immediate, pointed skepticism. Astronomers who had spent their careers chasing exactly this kind of result, and who had watched Van der Kamp's astrometric wobble collapse under scrutiny decades earlier, wanted more than a compelling data curve before accepting that the search was over. The most serious alternative explanation raised at the time was that 51 Pegasus apparent wobble might not be an orbiting planet at all, but a form of stellar pulsation, a rhythmic swelling and shrinking of the star's own outer layers that could, in principle, produce a periodic shift in its spectral lines resembling an orbital signal. Some kinds of stars are known to pulsate this way, changing brightness and even apparent velocity on regular cycles without any planet involved. Ruling this out convincingly required checking whether the star's brightness itself was changing in a way consistent with pulsation, which it was not, and it required an entirely independent team confirming the same radial velocity signal with different equipment. That independent confirmation came remarkably fast. Jeff Marcy and Paul Butler, running their own long-standing radial velocity survey at Lick Observatory in California, had 51 Pegasi in their own target list. Within about a week of hearing of Mayor and Queloz' announcement, they turned their instrument toward the star and within days confirmed the same 4.2-day signal, independently, using a spectrograph built by an entirely different team on an entirely different continent. That speed and cleanliness of confirmation mattered enormously, precisely because of the field's history. Van der Kamp's claimed planet around Barnard's star had taken over a decade to be seriously challenged and effectively never received a clean independent confirmation, only a slow accumulation of failed attempts to reproduce it. 51 Pegasi b was confirmed within roughly a week by a team using different hardware on a different continent getting the same answer. The contrast told the field everything it needed to know about the difference between an artifact and a discovery. The news reached far beyond the astronomy community. Newspapers around the world ran stories describing the discovery of a planet beyond our solar system, the confirmation of an idea that had been debated, in one form or another, since Bruno's writings 4 centuries earlier. Mayor and Queloz became, almost overnight, 2 of the most recognizable names in a field that had, until that week, worked largely outside public attention. The pulsar planets of 1992 had made headlines too, but 51 Pegasi b captured something different. A planet around a star close enough in nature to our own sun that people could imagine, however loosely, a version of our own solar system's story playing out somewhere else. Confirmation did more than settle one argument. It told every team running a radial velocity survey around the world that the technique worked, that the instruments built through the 1980s and early 1990s were finally sensitive enough to find real planets, and that whatever else was out there, among the stars each of them had already been quietly monitoring for years, was now worth a much closer look. Once the technique was proven, teams that had been patiently gathering radial velocity data for years suddenly had a reason to comb back through it. Marcy and Butler, who had already confirmed 51 Pegasi b within days, announced 2 further planets of their own within months, orbiting the stars 70 Virginis and 47 Ursae Majoris, using data their survey had already collected before 51 Pegasi b existed as a confirmed reference point. Almost all of the planets found in the first few years after 1995 turned out to be hot Jupiters, giant planets in tight, fast orbits, and this created a brief, mistaken impression that such planets might be unusually common throughout the galaxy. The truth was more mundane and is worth understanding, because it recurs throughout the history of astronomy. Radial velocity is far better at finding large planets in short, fast orbits than small planets in slow, wide ones, because a bigger planet produces a bigger wobble, and a faster orbit lets you observe several complete cycles in a reasonably short survey. Astronomers call this kind of skew observational bias, meaning the shape of the results reflects what the method is good at detecting as much as it reflects what actually exists. Hot Jupiters were not necessarily common, they were simply easy to find first. Through the late 1990s, teams steadily improved their instruments, pushing radial velocity precision down toward just a few meters per second, and eventually below it, allowing them to detect smaller and more distant planets that produced correspondingly smaller wobbles. The HIRAS spectrograph on the Keck telescope in Hawaii became one of the most productive instruments of the era, adding to the growing list year after year. By the end of the 1990s, several dozen exoplanets had been confirmed. By the mid-2000s, the count had passed 100. The pace of the change is worth stating plainly. In the more than 30 years between Otto Struve's original 1952 proposal and 1992, astronomers confirmed exactly one planetary system beyond our own, the pulsar system around PSR B1257+12. In the 10 years following the confirmation of 51 Pegasi b in 1995, that number grew past 100, a 100-fold increase achieved in roughly a third of the time. What had been, for 4 centuries, one of astronomy's most stubbornly unanswered questions became, within a single decade, a routine and expanding catalogue. The growing catalogue also began revealing genuine diversity beyond hot Jupiters, giant planets in long, elongated, eccentric orbits unlike anything in our own solar system, multiple planet systems discovered around single stars, and, as precision kept improving, the first hints of smaller, denser worlds that might not be gas giants at all. But radial velocity, no matter how refined, had a hard physical limit. It measured a planet's minimum mass and its orbital period, and very little else. It could not tell you a planet's size, its composition, or whether it had an atmosphere. Answering those questions would require watching starlight in a completely different way. That different way went back, in fact, to the second half of Otto Struve's original 1952 proposal, the half almost nobody had been able to attempt yet. Watching for the moment a planet passes directly in front of its own star. Struve's second idea, back in 1952, was almost embarrassingly simple in concept, even though executing it would take more than half a century of technological progress. If a planet's orbit happens to be aligned so that from Earth's point of view it passes directly in front of its star once every orbit, the star's light should dim by a small, precise and perfectly repeating amount every time that happens, then return to normal once the planet moves past. Astronomers call this a transit, the same phenomenon that lets observers on Earth watch Venus or Mercury cross the face of the Sun on the rare occasions their orbits line up. The challenge was the size of the dip. A planet the size of Jupiter, passing in front of a star the size of the Sun, blocks only about 1% of the star's light, a change bright enough to detect from the ground with a sensitive enough instrument, and the first transiting exoplanet, a hot Jupiter called HD 209458b, was confirmed this way in 1999, using ground-based telescopes, shortly after its existence had already been suggested by radial velocity data. But a planet closer in size to Earth, in front of a star the size of the Sun, blocks only a few hundredths of 1% of the star's light, a dip so small that Earth's own atmosphere, constantly shimmering and distorting starlight as it passes through, makes it essentially impossible to measure reliably from the ground. The solution was to leave the atmosphere behind entirely. NASA's Kepler Space Telescope, launched in 2009, stared continuously at a single patch of sky containing more than 150,000 stars, measuring each one's brightness with extraordinary steadiness and looking for the same tiny repeating dip over and over across years of uninterrupted observation. Kepler needed to see the same dip recur at least 3 times on a regular schedule before a candidate was taken seriously, both to rule out one-off events like a passing asteroid or an instrumental glitch, and to pin down the planet's orbital period precisely. Kepler transformed the field again, in much the same way 51 Pegasi b had transformed it 14 years earlier. Before Kepler, a few hundred exoplanets had been confirmed, most of them found by radial velocity, most of them large. By the time its primary mission ended, Kepler alone had contributed thousands of confirmed and candidate planets, and revealed that entire categories of world exist that have no equivalent anywhere in our own solar system. Super-Earths, rocky or partly gaseous planets larger than Earth but smaller than Neptune, and mini-Neptunes, smaller gas-rich worlds intermediate between Earth and the ice giants. Neither category exists among the 8 planets orbiting our own Sun, and Kepler's data suggested both are, if anything, more common throughout the galaxy than planets like our own. Where radial velocity and transit observations overlap for the same planet, they complement each other precisely. Radial velocity gives a planet's mass, transit gives its size, calculated directly from how much starlight it blocks and how large the star itself is known to be. Combine the two, and astronomers can calculate a planet's density, which tells them whether they are looking at a rocky world, a gas-rich one, or something in between, the first real step toward understanding what a distant planet is actually made of, rather than simply that it exists. Kepler's successor, TESS, launched in 2018, extended the same transit method across the whole sky rather than one small patch of it, specifically targeting bright nearby stars, where the resulting planets could be studied in more detail by other telescopes. Between the two missions and the radial velocity surveys still running alongside them, the trickle of discoveries that began with a single wobbling star in 1995 had become a flood. By the time Kepler, TESS and decades of radial velocity surveys had done their work, the question that occupied Bruno, Kant, Struve, van der Kamp, Wolfsjan, Mayor and Queloz across 4 centuries had not merely been answered, it had been answered so thoroughly that the answer itself had become almost mundane. Astronomers have now confirmed more than 5,500 planets beyond our own solar system, with several thousand additional candidates still awaiting confirmation. The catalogue includes far more variety than anyone in 1995 anticipated. There are hot Jupiters, like 51 Pegasi b, orbiting so close to their stars that a year lasts only a few days. There are super-Earths and mini-Neptunes, the 2 most common types of planet astronomers have found so far, neither of which has any counterpart in our own solar system. There are planets locked in orbits around 2 stars at once, evoking the double sunsets of a well-known piece of science fiction, but confirmed as physically real. There are even rogue planets, worlds ejected from their original systems entirely, drifting through interstellar space with no star to orbit at all, detected only through the brief gravitational lensing effect they produce when they happen to pass in front of a much more distant background star. Statistical analysis of the stars Kepler surveyed, extrapolated across the roughly 100 to 400 billion stars believed to populate the Milky Way, leads most astronomers to estimate that the galaxy contains, on average, at least 1 planet for every star and quite possibly several. Current models suggest the true number of planets in the Milky Way may exceed the number of stars, though the precise figure remains uncertain and depends heavily on assumptions about planet types, too small or too distant for current instruments to detect reliably. A number like that is difficult to hold in the mind honestly, so it helps to make it smaller and more concrete. If you could visit one newly discovered exoplanet system every single day, starting from the day 51, Pegasi b was confirmed in October 1995, you would still not have visited even half of the more than 5,500 planets astronomers already know about today, 3 decades later, and that catalogue, vast as it feels, represents only the planets close enough and favourably oriented enough for current instruments to detect at all, almost certainly a small fraction of what actually exists among the roughly 100 billion or more stars in our galaxy alone. The frontier has since moved from simply finding planets to studying them in detail. The James Webb Space Telescope, launched in 2021, can, for a limited number of favourably positioned exoplanets, analyse starlight that has passed through a planet's atmosphere during a transit, identifying which gases are present from the specific colours of light they absorb. Astronomers are using this technique to search for atmospheres, water vapour, and, eventually, combinations of gases that might indicate biological activity, so-called biosignatures, though no such discovery has been confirmed, and researchers are careful to stress that any candidate signal will require extensive independent verification before anyone treats it as evidence of life, learning, once again, the lesson van der Kamp's error first taught the field decades earlier. What began as a philosophical argument about whether the universe made sense with only one inhabited world in it has become an actual, growing map, and that map is forcing the same 4-century-old question into a new and much more answerable shape. None of this was ever really about a single star, or a single wobble, or a single number in a catalogue. It was about a question that outlasted every person who first asked it. Whether the arrangement of our own solar system, one modest star warmed steadily for billions of years, circled by rocky worlds close in, and gas giants far out, with at least one planet that happened to grow life, was special, or simply one configuration among countless others. The answer, built up patiently across 4 centuries of speculation, 3 decades of false starts, one strange discovery around the wreckage of an exploded star, and 30 additional years of accelerating confirmations, is now about as clear as anything in observational astronomy gets. Planets are not rare. They are, by every current estimate, the default outcome wherever a star forms with enough leftover material around it. What is rare, or at least remains unconfirmed anywhere else so far, is a planet like ours, rocky, wet, orbiting at a distance where water can stay liquid on its surface, around a star stable enough to let that condition persist for billions of years. Every one of the more than 5,500 confirmed planets in that catalogue was found, in the end, the same way Otto Struve imagined in 1952, without any instrument capable of testing it, by watching a star's light closely enough to notice that something else, unseen, was quietly disturbing it, a trembling in its colour or a fractional dimming in its brightness that meant a star was not alone. Every one of those stars had sat for centuries, as nothing more than a point of light among billions, indistinguishable from its neighbours, a number in a catalogue no one outside, a small circle of astronomers had ever bothered to learn, reading that trembling correctly, and only after learning, the hard way, how easily an instrument can fool a careful scientist into seeing a wobble that is not there, is what turned each of those anonymous points of light into a known and, in the fullest sense, a mapped solar system. In 2019, the Royal Swedish Academy of Sciences awarded Michel, Mayor and Didier Queloz a share of the Nobel Prize in Physics for that 1995 discovery, 24 years after the night it was made, an unusually long gap even by the standards of a prize that often waits decades to confirm a result's lasting importance. The delay was itself a kind of vindication. By 2019, no one seriously doubted that 51 Pegasi b was real, or that it had opened a field that, in less than a quarter of a century, had gone from a single contested claim to a working global science with thousands of confirmed results. What this means for the oldest question underneath all of it, whether anything else is out there, is still genuinely unresolved, and the honest answer is that astronomers do not know. What has changed is the scale of the search itself. 4 centuries ago, the question of other worlds was a matter for philosophers and theologians, argued without a single data point to settle it. Today it is a matter of instrument sensitivity and telescope time, a search being actively conducted, star by star, across a galaxy now known to hold more planets than anyone in 1995 thought reasonable to guess. Somewhere in the sky tonight, among the thousands of points of light visible to the naked eye and the billions more too faint to see, some unknown number are doing exactly what 51 Pegasi did in the quiet data of a French observatory 3 decades ago, trembling, almost imperceptibly, because something is there. Astronomers are still learning how to listen for it 1 star at a time, and the number of stars left to check is, for all practical purposes, still the whole sky. 400 years passed between Giordano Bruno's execution for suggesting that other stars had worlds of their own, and the October night when 2 astronomers in the French Alps found the first proof that he might have been right. In between lay centuries of pure speculation, a respected scientist who spent 30 years defending a wobble that turned out to be a bent telescope lens, a strange and violent discovery around the corpse of an exploded star that satisfied the letter of the question without quite answering its spirit. And finally, in 1995, a small, ordinary-looking star in the constellation Pegasus that turned out to be circled by a planet unlike anything in our own solar system. What makes that story worth telling is not just the planet itself, remarkable as it turned out to be. It is the method, the discovery that you do not need to see a thing directly to know, with confidence, that it is there. A star's trembling light, checked against every other explanation and confirmed independently by a second team, using a second instrument, was enough. That same patient method has since found more than 5,500 other worlds, and shown that planets are not the exception in this galaxy. They are close to the rule. What began as a philosopher's guess is now a map still being drawn, 1 point of trembling starlight at a time.